Bismillahirrahmanirrahim. In this video I will be solving end chapter problem 5.2, and this is on the request of a student. So let's see what is end chapter problem 5.2 or question 5.2. A 2300 volt 100 kVA 0.8 power factor lagging 60 Hz 2-pole Y-connected synchronous generator. So first let's see the Y-connected synchronous generator. The arrangement is something like this, and as I have been telling that whenever the voltage is given, the voltage is line to line. That means now this voltage is the terminal voltage or 2300 voltage, which is between two lines, and its reactances are given, and reactance and armature resistance. So this is the armature resistance and this is reactance. At 60 Hz, if friction and windage losses are given, these. The field current has a DC voltage of 220 volts. So this voltage, field current voltage. Now this is only one phase. We are representing it separately. And its maximum IF, that is field current, is 10 ampere. The resistance of the field circuit is adjustable over the range from 20 to 200. So this can be adjusted by this resistor. And the open circuit characteristics is shown in figure. We'll see that. And these are the 5 questions that has been asked. So we'll be solving one by one. Okay, so let's see the first question, part A. How much field current is required to make the terminal voltage Vt equal to 2300 volt when the generator is running at no load? So if you recall, this is the three-phase diagram, and this is open circuit curve. Open circuit terminal voltage is plotted here, and the field current is plotted here, and this is the data given. So this is the terminal voltage or line to line voltage. This is power factor, and the frequency and 2 poles. So we'll take help of the OCC graph. So this is the graph, and this is very simple. We'll just plot the remember, the OCC graph is always between the open terminal voltage, that is Vt, for the three phase, or Vt is actually line to line voltage, this one, and the field current If. So this is the field current. So from the graph, for 2300 volts, we see that the field current is about 4.3 ampere. So this is the first part. Now let's go to part B. What is the internal generated voltage of this machine at the rated conditions? So we want to find, this is the internal generated voltage at the rated condition. Now at the rated condition means that at the rated power and the rated output voltage and the rated current. So we have to find this current, we have to find the phase voltage. Now this is, for ease, we are considering only one phase. Okay, and this is the same data that is given. Okay, and from here you can see that EA is actually the V phi or V phase voltage multiplied by or plus the drop here and plus the drop here. So that is what is written here. V phase and the drop in the armature resistance and the drop in the armature reactance. So first of all we need to find what is IA. Now keep this in mind. I'm just repeating it. Let's clarify our concepts. Couple of things for the Y connection. The phase voltage is not same as the line voltage. They are different, but the phase current is same as the line current. Also, when we talk of power, the power is actually 3 multiplied by the phase power, and phase power can be written as V phase, I phase and cos of theta when we are representing the power in watt, which is the case in the output side of the circuit. Now for Y connection, V phase is actually V line divided by under root 3, and so our equation will become this equation. Now this you can remember for whether it is a delta circuit or it is a Y circuit. This is the formula for total voltage. Okay, now we want to find IA. So there are two scenarios. One is the power in watt. If it is given, then we'll use this formula under root 3 Vt IL cos theta. But if the power is given in kVA, which is towards the input side, then we will only use under root 3 Vt IL, not the cos theta. Now in this case the power is given in kVA, so we'll use this formula. So we know power given, and we know the terminal voltage, and we can calculate IL, which is actually IA also. The line current and the phase current are same. Okay, so from here we can say that IA, which is equal to IL, is equal to power divided by under root 3 VL from this formula. Vt is VL. This is given 1000 kVA, under root 3 VL or V terminal is given 2300 volt. So the current comes to be 251. Now this is the magnitude of the current. To use it in this phasor diagram, we have to find the angle as well, and the angle can be found from the power factor. So we know that the power factor is cos of theta. Therefore the theta angle can be cos inverse of 0.8, which is equal to minus 36.87. Because it is lagging, that is why we are putting the minus sign. Okay, so our current in phasor form will now be 251 and this angle. We'll use now this current in the equation here. Also keep in mind now that V phasor, V line is given 2300 from here. So we have to convert it into V phasor, and I'm just for my ease I'm saying that this is the rated voltage per phase, because this data is the rated values. So V phase rated will be 2300 divided by under root 3, so 1328. So we'll use this value in here. Okay, so EA generated and rated is the phase voltage V phi, and multiply the resistance given with the current and multiply the reactance given with the current. And if you use your calculator in complex mode, in simple one step you can find the answer. If you don't know, I have a video on this subject, so you can watch that video, how to use your calculator in complex mode. So anyway, this is the power that is generated for, in this case, in one of the generators. And for the single phase case, then we can say that this was the rated output voltage, and we know the current, so current drops, and this we calculated to be the rated voltage generated. Okay, so we were here, we got the rated voltage generated for this rated phase voltage. And now let's see the question, how much field current is required to make Vt equal to 2300 when the generator is running at the rated condition. Now this is disturbing me, so I'll just eliminate it. I'll put a cut mark. And basically the question is how much field current is required when the generator is running at the rated condition. And you know that for the field current we need two things, or we need actually the terminal voltage and we need the open circuit curve, characteristics curve. So this is the open circuit characteristics curve. If we know the open circuit terminal voltage, we can find the field current. So let's head for the open circuit terminal voltage. Now this is the generated voltage. So we want that when there is no load, this voltage should be at the terminal. So this is same when there is no load. So V phi is same as EA, and EA we had calculated 1537. Now let's go back, because this voltage is the line voltage and this is for the phase voltage, so we have to convert the phase voltage into line voltage. And we know this diagram for the Y connection, V phase and V line, and you know that V line is under root 3 times greater than the V phase. So V line no load we can say is under root 3, V phase no load, and V phase no load we have determined from here that it will be same 1537. So the V line no load now will be 2662 for this condition, because this was the rated condition. Now to maintain this rated condition, we have to generate the line voltage of 2662. And now we'll look at this diagram, the OCC. So for 2662, we need a field current of approximately 5.8, 5.9. Okay, so this is the same, the open circuit voltage, Vt open circuit. From here we're looking that. And so the line current is 5.9 ampere. So this is slightly tricky, but if you concentrate, it will be easier to find out. Okay, now let's move to the question number D. How much power and torque must the generator prime mover be capable of supplying? So I'm sure you all have an idea what is a prime mover. If this is the generator, the turbine, a steam turbine is a prime mover. So we need to find how much torque it will produce and how much power this has to produce to run the generator. Now, the input power to this generator is equal to the output power plus loss. We know from this diagram that the input power is output power plus these losses. And this is what is given as the rating, rated voltage, rated power, and also so the power output will, if we convert this kVA into watt, because output power is always in watt, so we have to multiply it by the power factor. So this is the output power in watt or kilowatt. And now the losses, the loss PCU or the copper loss, 3 times the loss of one phase. So we know RA, we know this current. So the copper loss is this much. We had calculated IA 251, so we are using that. This is given a friction and windage loss 24 kilo, and the core loss is 18 kilowatt. This is also given. So we are getting every copper loss we calculated from here and the core loss is here, and the friction and windage loss is here, and stray loss we can neglect since it is not given, so we assume it to be 0. So the input power now, adding all this, is 870.4 kilowatts. So this much power the turbine has to provide, or should be able to provide to run the generator. Okay, and then therefore the prime mover must be capable of supplying 870.4 kilowatt. Okay. Since the generator is 2-pole, a 60 hertz machine, its speed would be 3600 if we follow this formula. 120 multiplied by 60 divided by 2, so it will be 3600 revolutions per minute. And to calculate torque, we will need this value. We know the formula that the torque applied is power n divided by the rotational frequency in radians. So this was the speed. We multiply, or we divide it by 60 to get it in seconds, and multiply by 2 pi to get it in radians, and power n is the same. Therefore the torque generated by this prime mover is 2310 Newton meter. Okay, so I hope this is clear. Now we finally come to construct a capability curve for this generator. Now capability curve is a complicated topic. I'll not explain this, but I'll just give you an idea what all is required. The capability curve, the stator and the rotor heats up, and that limits the performance, together with any external limits of the synchronous generator. It can be expressed graphically by the capability diagram. So the first thing we need is we need to find Q from this formula. In the book it has been derived. And what is this actually? It is the rotor current limit of the capability curve would be drawn from an origin of, so this point gives the origin of the rotor current limit. Next, and all the values we have calculated, so we can calculate this. So this is negative 4810 kVr. Remember, this is the origin point. And so if we have a vertical scale like this, we come down from 0, we come to minus 4810. So this is the origin of the rotor current circle. Next we found the radius of the rotor current. So we have found the origin. Now we need to find the radius of any circle that we will draw from here, and that is given by this formula, and putting in the value, we find the radius to be 5567 kVA. So now we'll draw the radius from this point. So we'll take a radius of 5567 and we'll draw around. So it will be something like this. Only part of it we are showing with this radius. So this is the rotor current limit. So you cannot go beyond this. Now there is another point, and that is the stator current limit. So stator current limit is the circle at the origin of radius this. So this is the apparent power. So this will limit the stator current. And we can also calculate this value. We know all these values. So this is 1000 kVA. So we have to draw a circle of radius 1000 kVA from the point origin, from the here. So let's draw this. So it will be something like this. Now we cannot go beyond this, and we cannot go beyond this. So our final curve will be something like this. So this is the limit, or this is the capability curve. We have to stay within this capability limit. You can complete this circle as well. So this will be the limit actually. So I hope this gives you an understanding how you can solve this type of a question. Please give me your comments. Thank you.